Class, we are going to start a new chapter today called Coordination Chemistry. Class, before going into details of coordination chemistry, we must understand some basics. So, I have written here transition elements, first series, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. Atomic number, you all know 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. Class, if I want to understand coordination chemistry in a better way, I must have to remember the atomic numbers and their valence shell configurations that have been taught to you in class 11. See, scandium 21 configuration is 3d1 4s2, titanium 3d2 4s2, vanadium 3d3 4s2, chromium are exceptions, chromium and copper. So chromium 3d5 4s1 and copper is 3d10 4s1. Similarly, Zn is 3d10 4s2. Class, with this table, what we are going to do? We are going to find the valence shell configuration for M B positive ion, M bipositive ion, M tripositive ion. And what is the basic funda? Basic funda is that 4s electrons are liberated first. Class, we all know that 3d and 4s both have more or less same energy level, but during liberation of electrons, all transition metals liberate s electron first. So let us take example of scandium. Scandium or CD1 4s2, M positive 1. If one electron is out, it gives me 3d1 4s1. Similarly for bipositive, both the electrons will be out, it will give me 3d1 4s0. And similarly M positive 3 will neither have d electrons nor have 4s electrons, so it will be 3d0 4s0. In the next step, class, we are going to find out magnetic moment of M positive 3 ions. How it can be find out? This is the formula. Magnetic moment is always equal to root over n into n plus 2 Bohr megaton, where n equals to number of unpaired electrons. So class, in the first case, since there are no unpaired electrons, because we know up to argon all are filled, 18 electrons are already have been filled. So 18 up to argon, 19 and 2, 21. So total 21 electrons were there. But in tripositive ion of scandium, we find neither d electron nor s electron are present. Therefore, number of unpaired electron is 0. So 2 plus 0 gives you 2 and 2 multiplied by 0 gives you 0. Pm is called Bohr magneton, it is unit of magnetic moment. So for scandium we get 0 Bohr magneton magnetic moment. It will not show any magnetic property. Class, will have to fill up the entire table. Let us take example of iron. Iron is 26 3d6 4s2. After removing its first electron, it becomes 3d6 4s1. Remove another electron, it gives you 3d6 4s0. Now another electron, so now this time electron will come from 3d, so the configuration will be 3d5 4s0. And now class, we'll have to draw d subshell. We all know d subshell have 5 orbitals. And how many electrons are to be filled? 5. Follow Hund's rule. 1, 2, 3, 4, 5. Number of electrons we are getting 5. So I'll put here 5 plus 2, 7. 7 5 are 35. So I get my 4 magneton to 35 4 magneton. Class, let us take the example of copper. Copper is 3d10 4s1. M positive ion 3d10 4s0. Bipositive ion 3d9 4s0. Then tripositive ion 3d8 4s0. So now again you have to draw your d subshell. 5 orbitals. Never find in air, always draw. So how many electrons are there? 8. So we'll fill up 1, 2, 3, 4, 5, 6, 7 and 8. So how many electrons? Only 2. So I'll put the value here 2. 2 plus 2, 4, 4 to the 8. So the Bohr magneton is root 8 Bohr magneton. So students, if you want to understand coordination chemistry, this table should be filled up first. And how to fill? I have already told you that 4s electrons are liberated first. Go on writing their valence shell configuration. And since it has been asked magnetic moment of M positive 3, so whatever the valence shell configuration is shown here, Try to draw it here. Find number of electrons, and once you get number of unpaired electrons, you can put in this value, and ultimately you get your magnetic moment of M positive 3 ions. Now class, in the next topic, difference between double salt and coordination complex. What are the basic difference between them? Let us have an example on this. We are taking example of potash alum K2SO4, Al2SO4 whole thrice dot 24H2O, and let us one example of coordination compound Cr ammonia 6 Cl. This is your double salt, this is your coordination complex. Students, you will find that their way of writing the formula is different. Double salt, how can we define? Addition of two or more salt. Coordination complex, salts formed by donation of lone pair two metals by ligands. You will understand what are ligands. Ligands are lone pair donor with the help of coordinate bond. With the help of coordinate bond. There is no coordinate bond over here. See, ionic salt, water of crystallization. But in this case, we find that something is written in the square bracket. Ammonia is there, chromium is there, Cl3 is there. What are they doing? You will be understanding in 1 or 3. But for the time being, understand this one, that it is addition of two or more salt, and salt formed by donation of lone pair of metals by ligands. Ligands are lone pair donor with the help of coordinate bond is called coordination complex. Point number 2. When dissolved in water, they show test for all constituent ions. Let us take example. K2SO4 dot Al2SO4 whole thrice dot 24H2O. When you dissolve in water, they give you 2K positive ion plus sulfate and 3 sulfate, 4 sulfate ions plus 2 aluminum ions, and of course water is already there. So class, whenever we dissolve double salt, we'll get potassium ion in the solution, sulfate ion in the solution, and aluminum ion in the solution, and they will definitely show their test. But class, in the case of coordination complexes, they do not show test for constituent ions when dissolved in water. Let us take example Cr ammonia 6 Cl3. When dissociated in water, gives you Cr ammonia class, pay attention here, plus 3 chloride, and 1 chloride has 1 negative charge, so total how many charge on chloride? And minus 3, and if this is minus 3, then definitely this is going to be plus 3. So class, what we find? We find that it gives test for chloride ion only. Chloride ion only. No test for Cr, neither ammonia. So class, this square bracket is very stable. In due course of time, you will know that it is called coordination sphere, and coordination sphere is very stable. That's why coordination complexes are also very stable, and whatever the thing is there in the coordination sphere, they are not going to give you the test. So basic difference between double salt and coordination complex is that when dissolved in water, they will show all the tests of their constituent ions, but coordination complexes, whenever dissolved in water, they will never show the test for the ions or the metal which is enclosed in coordination sphere. because this coordination sphere is very very stable, and that's why coordination complexes are also very stable. So we can say that double salt are not so stable, but coordination complexes are very very stable. You will understand more as the theory goes on. So basic difference between double salt and coordination salt. So double salt, they show test for all the constant ions, but in coordination complexes they do not show test for all constant ions. Class, let us take example of coordination salt, Cr ammonia 6 Cl. Class, if I dissociate it, if I put in water, it gives me chromium ammonia 6 plus 3 chloride. So class, try to understand that just now I am going to give you Werner theory, but before we go to Werner theory, let us understand the entire concept. Class, since I am breaking this in presence of water, so Cl3 is showing primary valency. Primary valency. Because primary valency satisfied the oxidation number of central metal atom. This is your central metal atom, which will be accepting lone pair from ammonia. Class, since ammonia donates its lone pair, so ammonia is satisfying secondary valency. And class, this square bracket represents coordination sphere. In coordination sphere, we find only two things. One is your central metal atom, which is going to accept lone pair from molecules, also called ligands. I will give you the definitions. And Cl3 is certifying the primary valency because the charge on chromium is +3. Why the charge on chromium is +3? Let us find it out. Chromium, let's oxidation number is X. Class, ammonia is neutral molecule, no charge on it. So 0 into 6, and this must be equal to what? +3. So X equal to +3. So oxidation number of Cr equals to +3, and that +3 is being satisfied by 3 chloride ions. So Cl3 is satisfying the primary valency of central metal atom. Ammonia is giving lone pair to central metal atom, so ammonia is satisfying the secondary valency. Chromium is my central metal atom. Square bracket represents coordination sphere. In coordination sphere, we find only two things. Remember it always. In coordination sphere, we find only two things. One is your central metal atom, which is going to accept lone pair from ligands, and the ligands are there. So central metal atom, ligands are lone pair donors, and they are written in coordination sphere. Coordination sphere, non-ionizable, highly stable, and this coordination sphere makes coordination complexes highly stable. And in the next step, I have shown you how to find out the oxidation number of Cr. Simply break it. It gives you 3 chloride, 3 negative charge on it. Molecule is neutral, so if it is carrying -3 charge, then this entire complex will be carrying +3 charge. So chromium X, ammonia is neutral, so 0 into 6 will give you +3. X value you get +3. So oxidation number of Cr is +3. This was the basic to understand Werner theory. Now class, we are going to take Werner theory one by one. Number one, in coordination complexes, every central metal atom, CMA, central metal atom, exhibits two types of valencies. Number one, primary valency, and number two, secondary valency. Primary valency is satisfied by anions only. You see, primary valency is satisfied by negative ions, whereas secondary valency is satisfied by either anions or are neutral molecules. Primary valency is written outside square bracket because it is ionizable. Secondary valency is written inside square bracket. It is unionizable. Unionizable. Then point number 4. Primary valency satisfies oxidation number of CMA, whereas secondary valency satisfies coordination number of CMA. Coordination number of CMA. So class, what is coordination number? Coordination number equals to number of lone pairs accepted by CMA. So the number of lone pair accepted by CMA will give you the coordination number. So class, I repeat again. In coordination complexes, every CMA exhibits two types of valency, primary valency and secondary valency. Primary valency is satisfied by anions only. Secondary valency is satisfied by either anions or neutral molecules. In this case, you are showing by neutral molecules. In due course of time, I'll tell you about anions also. Primary valency is written outside square bracket. It is ionizable. Secondary valency is written inside square bracket. It is unionizable. You see, I have already written you coordinations here. It is not ionizable and highly stable. Primary valency satisfied oxidation number of CMA. Secondary valency satisfies coordination number of CMA. And what is coordination number? Number of lone pair accepted by CMA. So class, this was your Werner theory. Now class, we'll go for exercise here. Question is, find oxidation number, coordination number and number of moles on dissociation. That is also called Van 't Hoff factor. So we are going to find out this oxidation number, coordination number and number of moles on dissociation. Class, how to do? We'll first bracket. See, if I bracket, I know that we'll get 3 chloride ion here. So I'll write 3 chloride first. So 3 negative charge, molecule is exactly neutral. So this must be carrying positive 3 charge. Class, you know that coordination sphere is highly stable. It never breaks. So this is the situation now, and it has 3 positive charge. So if I want to find out oxidation number, I'll have to find oxidation number of chromium because oxidation number of, you can write here CMA, central metal atom. So let us take chromium equal to X. Class, ammonia and water both are neutral molecules, so they do not have any charge. So whatever the charge is there, it is already here. So no charge from this side. So the oxidation number of chromium is +3. Then coordination number. What is coordination number? Number of lone pair accepted. Number of lone pair accepted. So class, we know that ammonia will donate 1 lone pair. So there are 4 ammonias. So 4 lone pair will be donated by ammonia and 2 lone pair will be donated by water. Class, water donates only 1 lone pair. So there are 2. So 2 and 4, that gives you 6. 6 lone pairs are donated to chromium. Therefore, okay, this was your oxidation number and 6 is your coordination number. And class, to find number of moles, see 3 moles here and 1 mole here. So number of moles on dissociation is 4 and that is also your Van 't Hoff factor. Similarly class, we'll do it here. I know that potassium have +1 charge, so it will be giving me 4 K positive. And if it is 4 positive, then obviously this is going to be 4 negative. FeCN6, 4 negative. Now let us find out oxidation number of iron here. So X plus Class, this is cyanide and CNS minus 1 charge. In due course of lecture, you will understand what the charges are, because the next topic we are going to take up the charges there. For the time being, you all know that cyanide, potassium cyanide, K positive and Cn negative. So one cyanide has one negative charge. So how many cyanide are there? 6. So I'll take minus 1 into 6, and this must be equal to what? Minus 4. Next step, x minus 6 equal to minus 4. So x equal to plus 2. So oxidation number of iron is plus 2 here. Coordination number again 6, because one cyanide molecule, it is called cyano. One cyano molecule donates one lone pair, so 6 will donate 6 lone pair. So coordination number equal to 6. And number of moles on donation, 4 moles here and 1 mole here. So n equal to 5. So that is Vent-Hoff factor is also 5. Similarly, class, in this case, again let us break 1 potassium plus 1 charge, so 3 potassium 3K plus FeCl whole twice, Br whole twice, and Cn whole twice. And if there is 3 positive, then it must have 3 negative here. So iron, let us take X. Okay, they are called chlorido, bromido, and cyano. Each has minus 1 charge. Chloride, we all know Cl negative, 1 minus charge. Bromide, 1 negative on bromide also, and similarly 1 negative on cyanide also. So minus 1 into 2, minus 2, minus 2, minus 2 gives me minus 6 equals to minus 3. So x equal to 6 minus 3, x equal to plus 3. So class, in this case, again oxidation number of iron coming here plus 3. Coordination number. If 1 chloro donates 1 lone pair, 2 chloro will donate 2 lone pair. Similarly, 2 bromo will donate 2, and 2 cyano will donate 2. So 2 to 4 and to 6. Coordination number equal to 6. And class, number of moles on donation, 3 moles here, 1 mole here. So number of moles on donation is 4, and that is your Vent-Hoff factor. So class, this is the way to find out oxidation number, coordination number, number of moles on dissociation, and Vent-Hoff factor. Very, very important for your competition point of view, and to understand coordination chemistry also. Class, now we'll discuss some definitions. First is your ligands, which you are hearing from the very beginning. So ligands are lone pair donors. They donate lone pair to central metal atom, to CMA. Class, I repeat again, in coordination complexes, in coordination sphere, you will get only 2 things. One is your CMA, central metal atom, which accepts lone pair from ligands, and the second one will be your ligands who are donating lone pair. So in the coordination sphere, that is in square bracket, only 2 things are found. One is your central metal atom, another one is your ligands. Types. Monodentate, bidentate, and polydentate. Very easy to understand. Monodentate, 1 lone pair donor. Bidentate, 2 lone pair donors. Polydentate, more than 2. So first one, monodentate ligands. They can be further classified as anionic and neutral. We'll have some example over here. Cl negative is called chlorido. It donates only 1 lone pair. Similarly, bromido, cyano, all are carrying 1 negative charge. Iodido. Monodentate neutral. We have 2 examples here. Water called aqua and ammonia called amine. Why I am writing there in their name? Because while writing their IUPAC, these names will be followed. So go on remembering this, very important. Bidentate, two are very common. One is your ethylene diamine, CH2NH2, CH2NH2, one lone pair donor. So two atoms, two lone pair donors, but this is your neutral, no charge on it. Then we have one more oxalato. And it has two negative charge. How to write the formula? COO negative, COO negative. So one lone pair donated by this O and one lone pair donated by the second O. Now class, we have one example of polydentate ligand called EDTA, full form ethylene diamine tetraacetato. Ethylene diamine tetraacetato. Let us show the diagram here. So class, it's an example of hexadentate. Hexadentate. It gives hexadentate means 6 lone pairs. See how. First lone pair, second lone pair, third lone pair, fourth lone pair, fifth lone pair, and this is your sixth lone pair. So it is called EDTA, ethylene diamine tetraacetato, and it has 6 lone pairs as has been shown in the diagram. So class, note it down, very important. I repeat again, there are 3 types I have shown here: monodentate, bidentate, and polydentate. Mono, 1 lone pair donor; bidentate, 2 lone pair; polydentate, more than 2. Monodentate, 2 types, anionic and neutral. It is everywhere, you see, anionic and neutral. And this one is again the anionic. So anionic, chlorido, bromido, cyanohydrido, they all donate 1 lone pair. Water, aqua, ammonia is amine, they donate again 1 lone pair. Bidentate, 2 lone pairs, neutral. This is called ethylene diamine. Ethylene diamine. And the second one is oxalato, COO negative, COO negative. And we have taken example of polydentate ligand as EDTA, ethylene diamine tetraacetato, and the diagram has been shown here. 6 lone pair donor, 1, 2, 3, 4, 5, 6. So now class, we are moving to next topic, next definition. And that is your coordination number. Coordination number. Very simple. Number of lone pairs accepted by CMA is coordination number. NiCO whole 4. Ni has taken 4 lone pair from CO. CO is monodentate ligand, so 4 lone pair are being given. So coordination number equals to 4. Similarly, FeCO whole 5. So 5 carbonyl groups are there, denoting 5 lone pairs. Coordination number 5. And this we have already taken. So chlorido 2, bromido 2, and cyano 2. So each donating 1 lone pair. So 2 to 4 to 6. So again here coordination number equal to 6. So what is the coordination number? I repeat again, number of lone pair accepted by CMA is called its coordination number. Homoleptic complexes and heteroleptic complexes. Homoleptic complexes, such complexes having same legions. Same legions. See. So in the coordination sphere, we are getting 6 legions and all are ammonia. So that's why only same type of legions are there. So it is your example of homoleptic complexes. Different legions in the coordination sphere. So such complexes where the legions are different, they are called heteroleptic complexes. You see here, there are different types of legion. One is your ammonia, other one is your water. So homoleptic complex having same legions, heteroleptic complexes having different legions. Then chelate, very important. So when bidentate or polydentate legions surrounds CMA, central metal atom, in such a way to give closed, cyclic, highly stable complex. Such complex are called chelate, and the legion is chelating agent. So class, I repeat the definition again. When bidentate or polydentate legions surrounds central metal atom in such a way so as to give closed, cyclic, highly stable structure, highly stable complexes, such complexes are called chelate, and the legion is chelating agent. Example: CuEn whole twice SO4. Student, I am going to draw the structure. You see yourself. Ethylene diamine, one lone pair donated, second lone pair donated, because you know the ethylene diamine is bidentate legion. So 2 molecules are there. This one is another one, giving lone pair to copper. This becomes its structure. So now I repeat the definition again. When bidentate or polydentate, we have taken example of bidentate, surrounds CMA in such a way so as to give closed, cyclic, stable structure, highly stable structure. Class, you are seeing that the structure is closed, cyclic, and highly stable is that because coordination complexes are themselves stable, but due to this formation of cyclic, closed cyclic structure, they become more stable. That's why the word is used, highly stable complexes, and such complexes are called chelate, and the legion is called chelating agent. Here, ethylene diamine is chelating agent because it is surrounding CMA to give a closed cyclic stable structure.